This sections that I'll be presenting over the next 3 lectures I'll be giving is called Normalizing Flows, but I'm going to start a bit more broadly with the probabilistic generative modeling problem before we start talking more about normalizing flows. And then at the end, if you can stomach it, we'll be looking at variational autoencoders again. And we'll just revisit them, and I'll explain how and where we can slot normalizing flows in the context of variational autoencoders. So that's what we have in terms of roadmap for the next 3 sessions that I'll be giving. But like the other lecturers, I'm happy to take questions as we go along. I think I'm really not fussed if we leave out some of the stuff towards the end. It's kind of largely enrichment. So I'm quite happy that we pause and delve into things that you want to ask more about as we go along. So I've also peppered a whole little block saying questions as we go along to say might be a good time to be bringing in your question. If you want to download the slides and have your own copy and look through them, the link is at the bottom there of the slides, so you can type that in. I try to keep it somewhat memorable so that you can easily type it. So we're going to start off with probabilistic generative modeling, and I'm going to try and also every now and then pick up my phone so that I can see how we're doing for time. Because this is the context that we're going to be working in. So George Box famously wrote that all models are wrong, but some are useful. And this same George Box inspired the idea of Box's loop, which was presented in this paper by Dave Bly in 2014. And this captures the challenges we have when we are working with trying to build models, why we want to build models, and how we should be going about building these models and maintaining these models. So central, of course, is that we need a source of data with which we can train and evaluate our models. And generally, we're going through this process where we start off by hypothesizing or designing or deciding that maybe a certain model is appropriate for a certain kind of task. And the model on its own, when we combine it with data, if we design things well, should allow us to fit the model, learn the parameters, whatever the case may be, so that afterwards, once we have this model, we can deploy the model, okay? So that we can do things with this model. But if we simply train our model and deploy it without critically evaluating it, that can have disastrous consequences, okay? So if we want to be responsible, we're going to be critiquing our model, and that will often involve having more data. The simplest canonical example of this is having a validation set, okay, or a test set for evaluating your model. And often in real life, your source of data changes, things change in the real life, you have distribution shift, and then you've got to be able to pick that up. And this leads to a case where we might want to revise, modify, sorry about that, change our model, and then possibly update our hidden quantities. Also, we can just have situations where there's new data coming in all the time, and we want to continuously update these quantities and continuously critique the model. So that is the context that we have. And a lot of the talks we've been listening to have been talking about essentially the mechanisms of how do we infer these hidden quantities. And I'm going to be largely focusing in on that, but I think it's important to remember that context because we want to be identifying appropriate models and checking that they work in practice for the tasks that we have in mind. So generally, the reason we want to model is to answer questions related to the domain that our data is coming from. We want to apply our models. We're going to be looking at probabilistic modeling, and the aim with probabilistic modeling is to account for uncertainty. You can build models that aren't probabilistic, but when we do this, we can explicitly account for the uncertainty that we have and try and build robust solutions that are not sensitive to our uncertainty. Okay, so in general, this means our answers to questions should consider this density P of X, and yeah, X is just some observation that we are interested in, or x is just some value for a specific data point, and we are going to be interested in its density. So generally, we're just going to worry mostly about continuous variables today and tomorrow. So we're going to be interested in that density as opposed to mass in this case. And we would want to evaluate that. But also, for many, many tasks of interest, we want to know the expected value of some function of that variable x. Okay, and so that expected value is an integral where that f of x is weighted by the density p of x. And the simplest canonical example of this is if we want to work out the probability of something happening, then that function is going to be 1 when the thing happens and 0 when it doesn't, and we want to be able to integrate that. But we might want to know what is the average value of x, okay, or the variance of x. All these very simple ideas come back to we want to compute this expectation which corresponds to this integral. So the question is, how do we evaluate this integral? And I just want to put an aside here. I took out all my slides on what you can do with models, because Matthias did such a really nice job of that in the previous section where he gave lots of cool applications. So I'm taking that as read. We're going to be looking at the techniques here and just assume that if we can build these models and we can evaluate these expectations, there are lots of cool downstream tasks that we can tackle with them. So, expectations. There are 4 kind of main approaches that you encounter when you're trying to compute expectations. The one is analytic. So you sit down with your pen and paper, you derive the integral, you get a closed form solution, and you can work out the answer. If you're lucky, sometimes you can do that. In practice, rarely. Numerical integration. So if you want to do numerical integration, then you need to be able to evaluate p of x at very many different points. Okay, and if you have x is a high-dimensional object, the number of points you're going to need to evaluate it at is going to grow exponentially. So that is going to be a challenge. Monte Carlo estimation is another one. In this case, we need many samples from the density x. Okay, now that's going to require fewer samples, which is nice, but as a more difficult problem, we need to get samples from p of x. And then if you're in the more sophisticated Bayesian side, maybe you do MCMC estimation. Then you have this other complicated problem of designing a chain which has the p of x as a stationary distribution. That can be very nice, but it's a bit more difficult and technical to diagnose convergence, figuring out how many samples you need, and all that kind of thing. But when it comes down to it, all of these approaches at some point need us to be able to evaluate p of x or sample from p of x, maybe from a version of p of x where the p of x is not normalized. In other words, if we integrate p of x as a density or as a function, we may not get 1. Maybe we'll get 7, maybe we'll get 0.3, whatever the case may be, but it's not necessarily going to be 1. We can always take any function like that that's going to integrate to a fixed value and renormalize it to make it a density. Okay, so that fact is going to be relevant later on, but we always need to either compute p of x or sample from p of x. And if we're going to build models that allow us to sample from p of x, we're going to call it a generative model. Okay, so we're going to be looking at generative models primarily. So we're going to be focusing on situations where sampling should in principle be possible, although we will deviate from that later on. And if we want to actually do this, we need to find p of x. So we're going to have to not just compute the expectations, we need to know p of x, so we need to be able to learn it from the data. Okay, so these are the 3 things we want to be able to do. And one of the key things that's important for us is that we want our approaches to scale to high dimensions, because in modern applications, we have high dimensional data. You think of an image, okay, it's got 2,000 by 1,000 pixels by 3 channels or 4 channels. Okay, so that's already saying, now make that a video sequence. Okay, take an audio clip, etc. So we want to be able to model the distribution of those things. Okay, and we need to do it in a way that's efficient with respect to data and compute with time and memory. And this is very difficult to do just out of the box. So that's what our main challenge is going to be, is building systems that allow us to model in high dimensional settings. Okay, we also want the models we build to be flexible. It doesn't help building a model and we get a density, but the density doesn't reflect the true density in any meaningful way. And lastly, when we have latent variable models, which we'll only talk about probably tomorrow, we would like to be able to efficiently condition on the parts of X that we do observe. So if we have a partial observation. Okay. And when we do this inference, we would like to be able to get the conditional distribution in a way that we can also perform these key tasks with the resulting answer. Okay. If the resulting answer is a very complicated distribution, then it can be quite difficult to make progress. Okay, so within this, with all these requirements and desiderata and so on, there's a landscape of possible models. Okay, so this is the generative modeling landscape. I'm not going to talk about each of these different approaches. We have seen a lot of variational autoencoders as latent variable models. There's also graphical models, including Bayes networks, which we'll see a little bit later on. And we're going to talk a bit about how this can help us some of the way, but not the whole way. And then we'll be talking about normalizing flows in a fair amount of detail. Okay, Matthias spoke about diffusion models earlier, just before lunch. And then you've probably all encountered or seen GANs before, which are generative but not probabilistic in a sense, although there's an implicit likelihood. And then score-based models. So there's this whole gamut of possible generative models one can talk about. And certain models have got drawbacks, which I've kind of highlighted in red here. And this sort of motivates my interest in normalizing flows and variational autoencoders, because they've got fewer drawbacks in some sense than other ones. But your mileage may vary. Someone else would have a different list of requirements here and be interested in a different model. Okay, so normalizing flows are going to give us exact and fast density estimation, or that's the dream. With fast sampling, again, that's the dream. And VAEs will give us fast density estimation and fast sampling, but approximate density estimation, because we're going to be using variational inference, right? Okay. So I'm going to go back briefly to a situation where we have got discrete variables. Okay, most of the time I'll be talking about continuous variables, but just to illustrate this curse of dimensionality, I'm going to talk about a situation where each variable is a discrete variable and takes on a value from 1 to k. Okay, so in this situation, if there are capital D different variables, then an observation x, which contains all of these xd's, x1 up to xd, has a k to the d possible values. So if we don't make any assumptions about that distribution over those k to the d possible values, then we're going to need roughly to specify that distribution to specify k to the d possible values. Okay, and that's going to grow exponentially with d. So the more components that d has, maybe you think of them in terms of pixels of an image, the more pixels there are, I have a requirement of the amount of information I need to specify this distribution is going to grow exponentially with the pixels. Okay, and that is not something that is tractable. Okay, we don't have enough data for even moderate d for any problem. Okay, so we have to handle this data sparsity problem. And the key first step that we use is divide and conquer. So when you want to solve a problem or model something, one of the approaches we use is that we take the big problem, break it up into a number of smaller problems, solve each smaller sub-problem, and then in some way glue those solutions together to get a solution to the larger problem. Okay. So if we think of P of x as a function, one helpful way that we can break that down into smaller subproblems is if we think perhaps we can factorize that function or that density P of x. If we can write it in terms of a bunch of factors that might not involve all the variables, then we're going to be able to have smaller subproblems with less data requirements and so on. Okay, so once we have, if we can model each factor as a separate problem, then going back to P of X is easy. We just multiply those factors together. Okay, so if we can factorize and identify the factorization, then our problem subdivides into modeling each component. Okay, but how do we factorize it? Okay, so the natural starting point for factorizing a density is the autoregressive decomposition. So you guys should have seen this a few times, but just to remind you that from the definition for conditional density, we get the so-called product rule, which says that the density of two variables is the density of one multiplied by the conditional density of the other given that one. Okay. If we repeatedly apply this to the components of X, so yeah, we're taking X, which is a complicated object, and breaking it up into a bunch of parts. These could be individual scalars, but it could also be pixels in an image, or it could be images in a video sequence, where each X is a separate component, where each image is a separate component. Okay, so we can take the distribution over the entire X and decompose it into a product over the d components of the density for the small d component conditioned on the preceding d minus 1 components. Okay, and that's the autoregressive decomposition. It's general. We can apply it wherever we want. Okay, so we can represent this diagrammatically. So here we got x1, x2, we have an arrow coming in from x1, which means that x2 depends on x1. So when we specify the density for x2, it's going to depend on x1. x2 given x1. Likewise, x4 has arrows coming in from x3, x1, and x2. Okay, so x4 depends on x1, x2, and x3. Okay. So, let's say we decided we're going to do autoregressive modeling. It seems to fit the bill. If we can learn, evaluate, and sample from each of those conditional distributions, so that's not the same as the original, just learn a marginal distribution or distribution. We now have to be able to learn conditional distributions. If we can do that, then we can calculate the density for a specific x by computing each of those conditionals and multiplying them together. We can also use ancestral sampling to generate an observation, because we can, going back to this, I can sample an x1, then I can sample an x2 given that x1, then I can sample an x3 given x1 and x2, and so on. So autoregressive modeling formulates this, suggests that we consider the general problem of learning conditional distributions of some set or subcomponent of x given some other subcomponent of x. If we can do this, then if we can decompose our original density into a bunch of factors, then we can put them together. Okay. Does this address the curse of dimensionality? So we've got these factors. It seems like we're on the right track, but the downside is that last factor. What happens when we consider big D in this factor? Okay, that's the probability of the last component given all the other components before that. Okay, now if we go back to the situation where each of these variables has k possibilities, that last conditional distribution for any specific combination of previous values, I only need to specify k values for. So that looks good. But I need to specify k values for each of the k to the d minus 1 possible configurations of the other variables. Okay? And in that situation, I end up needing k to the d values. So I have the same curse of dimensionality that I had before. Okay, so the autoregressive decomposition seems to have promise, but ultimately it fails. So we need to address this somehow. And there are two broad approaches that get used for tackling this. And the one is excluding certain variable dependencies from the model. And that way lies Bayes networks that we'll talk about in a little moment. And the other one is to say, I'm going to constrain the form of each conditional distribution. my big assumption earlier was if we made no assumptions about the structure of the density, then we need this exponential number of values. If we make assumptions, for example, that things have a parametric form, we only need to learn the parameters for that parametric form. Far fewer values to be learned, needing far less data. Okay, so in terms of excluding certain values, it's literally a case of we're chopping arrows out of this diagram. So now, when we've chopped the arrows out, we have, for example, that we say that x3 depends on x1, but no longer on x2. x4 depends on x3 and x2, but no longer on x1. Okay, so if you're familiar with things like a hidden Markov model, you are throwing away all the previous time steps except the last one. That's a very aggressive form of this aggressive form of this kind of thing. So if you're doing time series modeling and you have some kind of Markov assumption, then you are essentially applying some structure like this. Okay, so for our sparse dependence, we need some sensible reason for chopping out certain arrows. Okay, you could just throw any randomly chopped out arrows at a problem, but that's not likely to necessarily work very well. But there are common assumptions, like the Markov assumption, that leads to allowing you to eliminate very many edges. Okay, so in general, when we assume that a specific component is independent of all the preceding components except for a small subset, we get that conditional density over there of xd given the preceding values is actually equal to the density of that value given that subset. And we use PA there to denote parents, because if we draw this as a graph and we think of the incoming arrows as parents, then we get what's called a directed acyclic graph, and that graph represents the dependencies. And the data we need in this situation, if you have discrete variables, still grows exponentially, but now it grows exponentially with the number of parents, not with the number of variables preceding it. And that means that if we can control the number of parents, we can control the amount of data that we need. Okay, so this direction leads us to probabilistic graphical models, and the models we're specifically looking at are called Bayes networks, which have got a variety of other names. But a key challenge with these models is identifying suitable independence assumptions. And there's a trade-off. The more independence you assume, the less flexible your model becomes, but the easier it becomes to learn, the less data you need. Okay, so Bayesian networks can, in principle, address our data sparsity issue, but the independence assumptions we make need to be reasonable. We're not going to go into designing Bayesian networks here. It's very important to realize that typically when we're applying these other tools like VAEs and normalizing flows and all these sorts of things, it's usually in the context where we've already made some underlying independence assumptions on the larger data that's coming in, and we are focusing on a sub-modeling task or conditional modeling task. We're modeling a specific frame given 2 or 3 preceding frames, or a given STFT given a history of the past few, and that kind of thing. Okay, so so first off, we're going to use something like a Bayesian network typically in practice to narrow down the specific data we're interested in. But secondly, once we've got that component, if we don't want to specifically say what the fine-grained structure of that component is as a Bayes network, we need some other way to learn that conditional distribution that isn't a Bayes network. So we need to be able to solve these sub-problems so that we can put them together. Okay, so how do we model those conditional distributions? Well, if these variables were finite, discrete, we could potentially build these little tables, but if the variables are continuous, we can't even do that. So we immediately have to start using some kind of parametric form or something, and that leads to constraining the form of each conditional distribution. So that's where we're going to be spending most of our time today, constraining the form of the conditional distribution in a certain way. So the key technique is parametric modeling. we want to say that this density looks like some kind of function, and that function has parameters, and we want to find the right parameters so that the function looks right or fits well. Okay, so in sophisticated models, so hang on, we are looking at estimating conditionals. We're trying to summarize the interaction between the XA and the conditioning variables XB. So XA given XB. In sophisticated models, parameters of the conditional are usually output by a neural network taking XB as input. So in other words, we are conditioning on XB, we have a network, we plug XB in, we run the network, and that gives us the parameters of the distribution for XA. Okay. Now, for that, we need to decide what the family of parameters, or what the distribution family is for XA given XB. And that's not necessarily an obvious thing. So if there's again a finite domain, there are 5 possible values, and they're not ordinal, they're just arbitrary, then you can say, okay, well, this is a categorical distribution, and so my parameters are going to be the values. This is basically setting up a table, like in the discrete case. If you've got a continuous variables, you need something else. So you might start with, oh, it's a Gaussian, and I want to predict the mean and the covariance, but that's not very flexible. So you say, let's make it a Gaussian mixture model. Okay, then we have to decide how many components there are, and there are all sorts of other complications. Okay, but ultimately, you are saying, I am positing some kind of family of distributions which has some set of parameters, and I need to learn to generate the parameters of the distribution for XA given XB. Okay, that's usually the situation right now. A lot of work has been done in this sort of space earlier, but they're all around this idea of, I assume that there's a certain form of distribution and I want the parameters. The problem is if we start going down very complicated Gaussian mixture models and stuff, it gets quite involved. But if we keep the distributions very simple, we can't necessarily fit things well. Okay, so if we view conditional distribution estimation as a general task, we don't expect the conditional distributions to necessarily fit simple parametric forms. So to tackle this problem, our aim is to investigate normalizing flows for general density modeling. And I'm not going to talk much about the conditioning aspect, but you should bear in mind that in practice, it's very often there. Okay. Yes?
When you now choose your family, let us say GMN. The question is not important enough for that. But no, I was just wondering, you have chosen your family, let us say GMMs, but then you have to multiply the components together, and that will take, well, that will either expand your family or take you outside the family. Is that when you multiply your different components together, or then let us say you have chosen GMM. So if you now multiply those factors together, your GMM will explode.
Yes, so I'm not going into that. So the Gaussian mixture examples were done very much in the context of doing this in an unconditional setting without having to assimilate it into a larger model. Okay, right. Okay, so any other questions at this point before we start delving into normalizing flows? I'm going a little faster than I anticipated, but maybe I'll slow down soon. Okay. So, roughly speaking, what are normalizing flows going to do for us? It's a little bit, there are vague links to the diffusion models that Matthias spoke about before, because at the one end of our normalizing flow, we're going to have some noise, and at the other end, we're going to have a complicated density, which is what he's done. But in the diffusion model setting that Matthias was speaking about, the way we got from the one to the other was by slowly adding noise and subtracting signal, roughly speaking. While in this case, we're going to be doing all sorts of interesting transformations, bit by bit, that we can undo. So we're going to design them so that we can undo them. Okay, or at least so that we know that they can be undone. Okay, well, when we're adding noise, that's usually not something we can undo. So in that case, in that sense, they're going to be different. So the idea here is we want to get a density that looks something like that, say, and our aim is to do that by learning how to stretch and squeeze and manipulate this distribution to get that. Okay, that's what this is all going to be about. Okay, but in such a way that we can go back there. Okay, now we're going to do this by composing a bunch of transformations in order, chaining them together and applying them just like we apply a sequence of functions when we take a forward pass through a neural network. So if we step only through if you take only 1 or 2 steps, we are going to be able to change this distribution only a small amount. If we take many steps, we'll be able to change it more. Okay, so part of it's going to be about deciding how many transformations do we need and can we get away with. Okay, so this was one of the earliest papers on normalizing flows that came out, where it was actually presented in the context of variational inference. Okay, but we'll come back to these in a while. So this is a preview of what we're going to be doing. So the idea is that this is going to be, sorry, these are 2 different kind of flows, by the way. This flow here is taking this and transforming it to this example here after 10 transformations. And the second part on the right is taking this and transforming it to this complicated distribution after 10 transformations. So the idea is that we want to model our conditional distributions by saying that our conditional distribution is some kind of transformation of a simple distribution that we understand well and can work with well. Okay. And the key part is going to be designing these transformations so that they are also things that we can understand well and work well with. And traditionally, actually, mathematically, there are not that many functions that we can work well with and understand well. And a lot of the progress in normalizing flows is all about expanding the collection of transformations that we feel comfortable working with. Okay, so normalizing flows at 30,000 feet, model joint distributions as a distribution is something which arises by taking a simple base distribution for variable z and applying a transformation. And the key thing is the transformation is invertible. I can go back to where I came from. And so I apply that invertible transformation to z, and that gives me x. Okay, so this simple base distribution z is something we want to be able to work with. So usually it's something that we can easily sample from, because that is going to be what is going to allow us to sample from the complicated distribution. And we want to be able to evaluate the density of it, because that is what's going to allow us partially to evaluate the density of an observation. Okay, now I will mostly use pz for the base distribution and px for the target distribution, because they'll both be floating around, and t for the transformation. And now the important thing here, because I'm going to have a lot of things going in opposite directions, is that t is always going from the base distribution to the data distribution. Okay, from the simpler distribution to the more complicated distribution. Okay, that's t. The network might not be modeling t, it might be going in the opposite direction. We'll see more about that later. Okay, but t, if I write t down, t is taking us from the base distribution to the complicated distribution. Okay. Now, below this, I've got a Bayes network diagram. So I'm going to explain a little bit about this, because some of it will come up with the VAE stuff tomorrow again, and so on. And so this is just to illustrate what's going on. So I've got these collections of variables. So first off, each value that's in this diagram doesn't necessarily correspond to just one scalar. It can be a complicated thing. Okay? So z here could be a very high dimensional vector. Okay? X could be a video sequence of 15 frames. Okay, something like that. Okay. Parameters are things that aren't enclosed in circles. So these are usually things we want to estimate, but we don't treat them officially as random variables for those that are more Bayesian around. Okay, and this little plate that we call this rectangle that goes around this denotes that there are independent, identically distributed copies. So this is saying that there are n copies of this in my context. And what is this? This is n different observations. So this is n IID observations. And each of these n has a corresponding underlying z that comes from a base distribution. And that is a variable that I don't see. You can think of it as a latent variable, right? Xn is something I see. But importantly, I'm assuming that Xn is obtained from Zn by applying a transformation, right? That I can go back along. So Xn is a deterministic function of Zn, and that function is represented by t. So this says that I can work out Xn if I'm given Zn and t. So if you think of Zn and t as parents, then that allows me to get Xn. And I can do that for each observation. Right. Okay. That is the data that I have. In general, I'm going to be interested in situations where I haven't observed something yet. Okay? So on the left, this X is not shaded because it's not observed. These Zs are not shaded because they're not observed. But I might be interested in saying something like, what is the distribution of this X? In fact, that is the learning problem, right? I want to estimate T so that I can say what the distribution of X is about. Okay. So a very, very simple situation might be that I say, if I assume that my X was a Gaussian, a simple scalar Gaussian, okay, then I could generate the X by taking a standard normal Gaussian with mean 0 and variance 1 and applying an affine transformation. I multiply by the standard deviation and I add the mean. In that case, the parameters of my transformation T would be mu and sigma. So T, if I think of them as a set of parameters, is just mu and sigma. But when we're writing, we'll often write T for the set of parameters, but also for the function. Okay, so yeah, I'm applying the function T to Z. In other words, I'm transforming Z using mu and sigma. Okay. So that is the setting. Our aim is going to be leverage the data that we've got to try to estimate T so that we can say something about the density of X. And also so that we can generate new X's. Okay, now I said we're not going to really be focusing on the conditioning side, but just to be aware that in the broader situation, we are usually dealing with conditional normalizing flows, which means that the transformation that we need to apply to get a specific XA from the Z is going to depend on the XB. And the way we're going to get those transformation parameters for a specific observation is going to be using another neural network that we train to take XB in and deterministically generate the transformation parameters we need, and then we can use those transformation parameters to generate XA from the base distribution, and I have to generate it so that this transformation is invertible. Okay. Now, a very important point, which quite significantly limits applying normalizing flows that you always need to be aware of, is that when we are trying to apply normalizing flows, if we want a function to be invertible, we need the range and the domain of the function to have the same dimension. Okay? I can't take a two-dimensional vector and map it into 3 dimensions and then necessarily invert that function, because if I take a plane and I transform it into three-dimensional space, I'm not going to be able to fill up the three-dimensional space, and there are going to be points in the three-dimensional space that I can't go back from. Does that make sense? Okay, so I need this correspondence of dimensions. If I want to get rid of that, I need some other techniques. Okay. This means that when we start with x, and x is a complicated thing, z is going to have the same dimension as x. So if x is a big image, by default, z will also be a very long vector. There are techniques like multi-scale architectures and stuff that allow you to try and work your way around those, but we'll see later that what we're actually doing is we're doing more other modeling and eventually leaving us with a smaller normalizing flow problem. Okay. So if we think about our key modeling tasks, sampling and density estimation, and we think about them from the perspective of normalizing flows, let's assume that somehow someone has given us the T, the transformation that we need, and for the sake of convenience, they've also given us T inverse. So we can apply T and we can apply T inverse as much as we'd like, and it's easy and it's effective and it's efficient. How do we sample and how do we do density estimation? Okay. So to sample, I want an x. My model is saying that the distribution of x comes from the distribution of z and applying the transformation. Z is chosen to be simple so that I can sample from it. So to get an x, I sample from z, and then I apply the transformation t. I'm assuming I can do that for now. Okay, so to get an observation, I pick something from my base distribution, and I transform it with t. Okay, so sampling would be easy. How about density estimation? Well, for density estimation, I start with an observation. Okay, so I've got this observation. I have T inverse, so I can find out what point in the underlying Z space corresponds to that. It's invertible. There's only one point. And so I should be able to just go back and then say, okay, there's the density. But unfortunately, when we apply transformations to densities, we change the density. We'll do an example in a moment. So the key component for normalizing flows, to really get them at the real core thing, is understanding how density of a distribution is affected by change of variables. Okay, so if you've done MathStats 2, you will be comfortable with this, or something like that. If you've done change of variables in calculus, which you probably have, you've seen the key idea, but you might not have assimilated it in this way. Okay, so in our context, we are going to be limiting the functions we look at to things that are called diffeomorphisms. Big fancy word. It means that the function is invertible, but also that it's differentiable. And the differentiability is important because we're going to be taking the derivative. And also because we want to use the inverse, we want that to be differentiable too. So we want the inverse to also be differentiable. So this is a function that's invertible and is differentiable in both ways. That's just the term, diffeomorphism. Okay, so sampling is fine. Density estimation is going to involve the density in the base distribution of the inverse image of the data point we're interested in, but a little bit more. Okay, so let's quickly look at scalar change of variables for linear. A linear scalar change of variables. So let's keep things simple. Z is a uniform distribution between 0 and 1. Okay, so the density of Z is 0 everywhere except between 0 and 1, and there the density is 1. Okay. I'm going to say that the transformation I apply, very simply, is I take that Z and I multiply it by -2. Okay, so what is the distribution of X going to be? Well, X is going to be uniform between -2 and 0. Okay, is there anyone that doesn't get that? Okay, because we must make sure of this. Okay, if X is uniform between -2 and 0, its density has to be constant between -2 and 0, right? And it's got to integrate to 1. So it's got to be a half everywhere between -2 and 0. So this says that if I picked a specific value, like a specific observation, minus 1.5, and I said the way I want to work out the density of that minus 1.5 is to apply the inverse transformation of multiplying by minus 2. So I divide by minus a half to get, I think, 3/4. Oh, my mathematician friend is just verifying, okay? And then I say, well, what's the density of 3/4 under the uniform distribution? I say, oh, it's 1. I get the wrong answer, right? I haven't catered for the fact that when I scaled from 0 to 1 to minus 2 to 0, I had to spread that mass out that was earlier between 0 and 1 over a wider interval between minus 2 and 0. Okay. So I need to take into account this change in density, and the change in density formula we use takes this derivative into account, and this is something that you will have seen as soon as you did change of variables in calculus when you're trying to compute integrals. Okay, it's exactly the same result. So we're taking the derivative of this inverse transformation with respect to x, okay, and we're taking the absolute value because I need the density to stay positive even though I'm multiplying it by minus 2, right? So I don't want the minus to sneak in. So there's an absolute value which is keeping things positive, and there is this derivative which is basically constant in our case. It's always going to be minus a half. Okay. When we have got a function that is not linear, then you should be aware that this thing is not going to be constant anymore, right? So we're going to need to deal with situations where that isn't constant, but we're going to use the same idea, okay? That the density of x is the density under z of the inverse, modified by an extra factor that takes into account how much we are stretching the mass in that location. Okay. So at any point z, a small interval of width, delta z, gets mapped to an interval of width twice the size. So that the mass that's on that little interval now needs to be spread out over a section that's twice as long, and that means we need to halve the density. Okay. If we move to high dimensions, we suddenly get thrown with this thing from linear algebra and multivariable calculus, and you are overwhelmed perhaps. Okay. But it's important to realize that all we're doing here is we're working out a bunch of little partial derivatives of inverses of t with respect to different variables. Okay, so we're taking components of x, and we are working out their partial derivatives. Okay, and that thing we get out is a Jacobian, and if you've done any multivariable calculus and had to do change of variables, this thing popped up. It's the same one. Okay. But this thing is not a scalar. Okay, it's not like this derivative that I could just take the absolute value of and then multiply it. It's a matrix. What do I do with this matrix? So I've got to replace the derivative by this thing, but I need something more. Okay. The key thing to understanding what we do with this Jacobian is to remember that what we're trying to do here is we're trying to take how big something is before and after the transformation and figure out what is the scale change and then factor in that scale change. So the question is, if I am stretching, according to this Jacobian, certain components by certain amounts in certain directions, which is what this Jacobian is doing, how can I say how much stretching is happening? Okay, that's what I would like to do. So, before we speak about how we know the amount of volume change, I just want to explain or mention that Jacobian that I just sort of pulled out of nowhere and said was a generalization comes out when you do a Taylor series expansion for your function, okay? So it's saying that very roughly, if you have this function t inverse and you take its Jacobian, then your function looks a lot like, whatever your function is, it looks a lot like a linear function around that point x. Okay, it looks a lot like a linear function, and the matrix representing that linear function is the Jacobian. So at a very local point, you're doing something a bit like a linear transformation. Now, how are we going to get out how much this is stretching or compressing the space? Okay. The key component we use to understand this is the singular value decomposition of the Jacobian. Okay, now, I don't know how many of you have encountered the SVD. I'm holding thumbs that everyone has seen it, but I understand that you may not have. But for now, I'm going to just go with that. And I'm going to note that because we assume that the dimension of x and z are equal, so that we have an invertible transformation, this Jacobian is going to be square, and that means these three components are going to be square. Okay. Now, I'm taking this x locally around x. I'm doing something that looks a bit like a linear transformation. And so if I take a small little volume around a point and I apply my transformation, I'm applying a linear transformation to that region. Okay, now, the SVD has three components here which roughly correspond to U and V model how I rotate the data and possibly reflect the axes. Okay. Key thing is when I rotate data, I don't change or stretch the volume at all. When I reflect an axis, I don't change the volume at all. So U and V are not going to play any role in terms of telling me how much I'm stretching the space. But what does tell me about how much I stretch the space is the sigma in the middle, which has what's called the singular values of the Jacobian in them. And each of those corresponds to a scaling factor that I'm applying in a different direction. So now what you can think of is if I had a two-dimensional situation and I stretched in one direction by a factor of 3 and in the other direction by a factor of 4, then I'm taking that little bit of volume and I'm stretching it out by a factor of 12. Okay. So in this case, this sigma, which has the singular values, is a diagonal matrix, and it's got all those stretching factors on the diagonal. So what I want to do is I'm going to multiply all of those diagonal values together to tell me how much I'm stretching things. Okay. So the actual stretching factor I'm interested in is the product of these singular values. Okay. And the product of the diagonal entries of a matrix, that is a diagonal matrix, is its determinant. Okay. So the determinant of the Jacobian is going to be important because the determinant of the Jacobian is going to correspond to this determinant of this diagonal matrix that we've just generated from the Jacobian. Why? Because the determinant of a product of a matrix is a product of determinants of the components. And U and V's determinants, it turns out because they are just rotations and reflections are orthogonal matrices, which by definition have determinants of 1 or minus 1. Okay, so in other words, the determinant of this Jacobian is plus or minus the determinant of that singular value matrix. Okay, and so if we want to know the stretching factor, we can take the determinant of this Jacobian and take its absolute value. That's our answer. The determinant of sigma that we're interested in is the absolute value of the determinant of the Jacobian. And we're going to wrap up in a minute because this is really the key thing that we are working towards. Okay? We know that to do sampling is going to be easy. We're going to sample, we're going to run forward, we're going to get our point using T. If we want to go back, we can work out the distribution, the base distribution of the inversely transformed observation, but I need to account for how much stretching is happening. When I have a high dimensional space, that stretching is going to be quantified by the absolute value of the determinant of the Jacobian. And that's the argument we had here. You don't need to remember the argument now, because we are going to focus later on how do we work out this Jacobian determinant, but that is the key component that we need to take on more complex distributions. So our general density estimation, if we want to know the density for an observation, I take X, I push it through my inverse transformation. That gives me something for my base distribution, so I work out its density. And then I scale that value, absolute value of the determinant of the Jacobian. Okay. And it turns out, with a little bit of math, that you can also work out the determinant of the Jacobian with respect to t instead of t inverse. But we won't use that very much, so I won't emphasize it now. Key thing, if we want to do this, we need to be able to evaluate t inverse of x. Okay? To do density estimation, I need to start with x, but I need to go back to the base distribution. So for density estimation, I need to be able to evaluate t inverse. T is the transformation that we're interested in. For density estimation, I need to be able to work out t inverse. Okay, and I'm going to finish up now for a bit. I think there's a tea break in a moment. But any questions before we break up at this point? Yes?
So you were mentioning that you need T inverse and you can't change the dimensionalities when you're doing the transformation. Otherwise, you can't have that inverse. But you were mentioning that there are tools that could allow you to do that if you add them into your architecture, which I assume you would do if you wanted an even more complicated, or to model an even more complicated distribution. Is it typical to do that? What are those techniques? Or is it, can you just get with the vanilla normalizing flows quite a lot?
So vanilla normalizing flows doesn't do the dimensionality changes, but initial techniques for doing that were introduced fairly early. So one of the techniques we'll be talking about is real NVP. We won't say much about it, but that was initial attempts at applying normalizing flows directly to images. And one of the key aspects of that was these dimensionality reduction approaches. Notably that when you reduce the dimensionality, you do still have a corresponding Z for each value. You just don't model all of them to the same level of detail. It's a little bit like having skip connections in a neural network. Okay, so multi-scale architectures is the thing you want to look up. Okay, right.
So my question was about the existence of the inverse of t. I'm not sure if I understood. What do we need to guarantee the existence of the inverse?
Okay, so that's the part we haven't spoken about yet. The question was, how do we know that t's inverse exists, basically? And the key thing is that for a normalizing flow to work, we need t's inverse to exist. And so we're going to design the functions that we try and fit in such a way that they do exist. Okay, so some early models, they had certain sets of functions, and if you chose the wrong parameter values, you wouldn't be able to come back. And that would have been problematic. So then they had to do extra work to kind of bypass that. But yeah, we're going to choose it so that those functions are invertible by design. And then we may later have situations where we know that they are invertible, even though we can't actually efficiently compute the inverse. Okay.
I see. Thank you.
No worries. Any other questions at this point?
Okay, if no questions, Steve will continue after tea time.